In the last lecture, we have answered some questions with respect to the Bitcoin, and we have seen these questions with respect to our regular example, that is the transaction between two parties when money is involved in a distributed and decentralized environment. So in which the first question is how the stakeholders will know the transaction initiation, that is by using flooding. The flooding and how this particular transaction initiation will be done in Bitcoin, how flooding will happen, and how the peer nodes in the network will listen. These concepts we have seen in the last lecture. And also we have seen how to verify identity of Ramu and Gopal, that is using public keys. Okay, that public keys, how we will use the public keys and how address will be generated, and then how the Bitcoin wallets will generate this address in the form of QR code, and what are the different type of wallets that will make us that can be used for working with these public keys and private keys. These concepts we have seen in the last lecture. So today we'll see some the things like how to ensure that only Ramu initiated the transaction, and how to verify the current balance of Ramu, and these concepts we'll see in this lecture. How to verify the balance. If you consider a general ledger transaction, and keep on writing like create 25 coins to credit to Alice, okay, and this is also asserted by miners, and transfer 17 coins from Alice to Bob. So first 25 coins was assigned to Alice. So this Alice, what he did is transferred 17 coins from Alice to Bob. Alice has sent 17 coins to Bob. So since the Alice is sending 17 coins to Bob, obviously this transaction must be signed by Alice. So signed by Alice. Next is transfer 8 coins from Bob to Carol. So here Bob has received 17 coins from Alice. So from this 8 coins was sent to Carol, and transfer 5 coins from Carol to Alice. So 5 coins, that means out of 17, 8 was deducted. So 17 minus 8 is 9. From that 9, 5 coins was sent to this one, this Alice. Now transfer 15 coins from Alice to David. So Alice has 5 coins at present, and previously 25 coins are there with the Alice. From that 17 was deducted. So 17 minus that is 25 minus 17 is 7, and plus 5, 12 coins only. That means currently the Alice is having 12 coins only, but Alice is trying to send 15 coins to David. So is it a valid transaction? How we will come to know? Whenever you write in a sequential order like this, it is very difficult to identify. The main problem with this, only one transaction per block, assume that. If it is so, then it is also very difficult, because if you write everything in a sequential fashion like this, without having any reference kind of thing, so it is very difficult to understand whether really Alice is having 15 coins or not in his account. That is, for this what they are supposed to do is, they need to go everything in backward. They need to check each and every record from into backward. Sometimes this assigning of 25 coins to Alice may happen 2 years back. From that Alice might have not done any kind of transaction, and recently he did it. That means the miners has to search how many transactions, that if you assume, then they have to go through almost all, some thousands or sometimes lakhs of transactions like this. So that is the reason it is a very, very difficult problem for verifying of the balance. So the easy solution has been used in the Bitcoin, that is via like this. So over a period of time, first of all, input, the transaction based ledger in Bitcoin will be like this. Input null, that means it is a starting input, that is a starting transaction. Output is 25 to Alice. This, based upon this input, this transaction is happening. So 1 of 0, this is the first transaction. On this first transaction, this transaction is happening. So 1 of 0, this was splitted to 17 and 8. 17 was given to Bob and 8 is given to Alice. So this splitting was signed by Alice. Now the address was changed. Alice's address was changed here, because the Alice, this particular 17 was given to Bob's address, 8 was given to Alice address. This Bob is, see, previously 25 is with Alice. Now it was splitted to 17 and 8. 17 was given to Bob. Now 8 was given to Alice. So how is it possible it was given to Alice? So that means Alice can have, first Alice will be having the public key and private key, and Alice can have any number of public keys as he want, because we have seen in the last thing that if you have a public key, you can generate any number of alternate public keys of your choice. So what Alice will do is, already he is having 25 bitcoins. What he do is, he will split this 25 bitcoins to 17 and 8. 17 he will send to Bob, and 18 he will send to the same public address. That means whatever the public address he generates, another public address to the same address, to that particular address, he will send it. That means this will become a transaction, and this will become a transaction. So 17 will be sent to Bob. Obviously Alice is having 25, so automatically this will be verified whether 17 is the sufficient balance he is having or not by any miner. So if it is satisfied, this transaction will be executed. Now 8 will be sent to Alice self address. Okay, it is just like how in the bank what you do is, if you have any check, pay to self. Okay, pay self. That means this amount will be given again to your account only. It is just same kind of trick will be played here. The 8 bitcoins will be sent to the same address. So this will also be considered as a transaction. Any miner will want to verify this. Obviously this 8, okay, after 17 deduction, 8 was rest available. So this 8 is belong to Alice. So again this 8 will be credited back to the Alice account. Now from this second transaction, in second transaction second block, 2 transactions are there. One is this one and this one. Now with this second transaction, first one, that is 0th one. So from this 17, 8 was sent to Carol, and since 8 was sent to Carol, 17 minus 8, so 17 minus 8 was sent to Carol. So what could be the rest of the things? 7 to Bob. So 8 to Carol and 7 to Bob. So now it was signed by Bob. So as it was done with the Alice, the same trick will be played with the Bob also. Self, it is paying self, and 8 was sent to Carol. Now this one inputs 2 of 1. That means from this 1, that is 0th. This is 0th transaction, and this is the first transaction. From 2 of 1, that is from this transaction, what is happening? 6 was sent to David, and 2 was with Alice. So but with 2 of 1, only 8 is there. From this 8, 6 was sent to David. So that means remaining leftover is 2 only. 2 is to Alice. So now how to find is it a valid transaction or not? In this block, it was given that input, this particular input was taken from 2 1. So go to the block 2, and what is the first transaction? This is 0th transaction, and this is the first transaction. This is the first transaction. From this first transaction, 8. Now you check these transactions. In 2 1, it is the 0th transaction and first transaction. Check whether this 6, that is the bitcoins which is sending to David, is less than 8 or not. Okay, it is less than 8. So if you deduct from 8, 2 is left over. So now this 2 will be again traded back to the Alice account. So this is the finite scan to check for validity. But in case of previous in the previous representation, there is no referencing from where to where you are going. You are supposed to check each and every transaction till you find the related transaction. But here, assume that this is the block and one transaction is there, some transactions are there. So next transaction is happening with respect to the first block, first transaction. This is the way referencing will be done. So this 2 1, that is second block first transaction, this is the one. Second block 0 transaction is this is the one, and first block 0th transaction is this is the one. So if I want to verify this transaction, I have to go through this. So what is this particular thing? Input first block 0th transaction. Now go to the first block 0 transaction. Like that, if the Alice has done any transaction after 2 years, so obviously what could be the input he has to make, whatever the transaction, whatever the block in which he is having the previous balance, from that block he has to refer. So obviously from that block, which transaction, and from which transaction you are going to make this particular next further transactions. So this is we implement this with the hash pointers in case of Bitcoin. In this way, splitting of the Bitcoins will take place, and if you want to send some amount to anybody, you will create a transaction of sending to somebody, and remaining is to your same address, that is pay to self. So the remaining balance will come to your account only. This is the way the transaction ledger will be maintained, and whatever the 17 is there here and 18 is there, which are not spent afterwards. So from this unspent transactions, you are getting this particular output. So this is what called unspent transaction output. This is called UTXOs. So from which block, which account you are drawing the transaction, from which block, which transaction you are drawing the account, which are not spent so far. From that you are making the amount that you want to send to the another party, and you are going to prepare this. So this is what we call unspent transaction output, and because of this hash pointers to the previous blocks and corresponding transactions, it is very easy to verify it. So this is the way, using this transaction based ledger in Bitcoin, the cross referencing can be maintained. While coming to the merging value, this is related to splitting value. I told you merging value is like this. So input output 17 to Bob and 8 to Alice, and from input first block, first transaction 17, 6 to Carol and 2 to Bob. So now from this unspent transaction, that is 17 to Bob and 2 to Bob, if you combined, the Bob will be having 19 transactions. This is called unspent transactions. So if you combine this, so automatically this one. So whenever you want to have the balance, obviously this is reference to the same public address of Bob, and this also reference to the same public address of Bob. So whatever the previous transactions are there, if it was executed or if it is validated miner, then this amount will be credited to this address, which is belong to Bob, which is a public address, and 2 is also credited to the Bob's address, which is also public address. So finally these two will be combined and will get into the third block. So 19 will be 19 Bitcoins will be held by Bob. So this is the way how the splitting and merging of Bitcoins will be maintained, and how the hash pointers to the transaction with respect to blocks will be maintained in the Bitcoin. And 2 members can perform the joint payments, like 17 to Bob, 17 Bitcoins will be held by Bob, 8 by Alice, now 6 by Carol and 2 by Bob. Now second block first transaction, 0th transaction, that is 6 to Carol, and second block first transaction, these two which are unspent so far, these two can be combined, and this will be sent to David. So this, for this, if two people want to contribute some amount to some person, some other party, then they can combine like this. But whenever they combine this, the signature of Carol is also required, and also signature of Bob is also required, because this 6 Bitcoins was taken from Carol account, and the 2.0, that is 2 Bitcoins was taken from Bob account. So that is the reason signing of Carol and signing of Bob is also required. It is just like whenever the joint account is there, if you want to draw money, that means at least if there are 4 joint members in an account, at least 2 or 3 members signature is required to make the transaction. So sometimes some banks will say that all joint account holders should sign on this, otherwise it is not possible to conduct the transaction. It's just like this. Whoever is the owner of the Bitcoin has to sign to have the joint payments. So how usually this will be remembered in the Bitcoin? In the Bitcoin, the metadata will be maintained like this: hash, that is the hash value, version 1. This one, this is called version relation information, and lock time and all, how much time it was locked, and housekeeping. This is the size of the transaction, the details, transaction hash. This is like a JSON file, it will be maintained. And so what is the input transaction? What is the input transaction? That is previous out, from which hash it was referenced. And here script signature, again it is in the hash you will be having. So this is related to the previous transaction, and this is a signature. So script signature, this is the signature signed by the person who initiated the transaction, and some more inputs. If you want to make a joint payment, this is the first input. You have seen previously, if you make joint payment, you got the transaction like this. This is the first from the second block, 0th transaction, second block, first transaction. So these two was combined. Like that you can have any inputs like this. And output. So output value is how much is the Bitcoin that you want to send. For example, 10 Bitcoins you want sending, and 0.1222286. This may be the mining fees or transaction fees that will be added. And script public key. See, this is the Bitcoin script. So this will be automatically generated whenever a transaction is initiated. You don't need to write anything. The Bitcoin script is like your assembly language code in microcontrollers and microprocessors. So this is operation DUP, and operation hash. So this is the hash value. Operation equal verify, operation check signature. So this is a Turing. This is a kind of hash code. This is a kind of machine instruction kind of script. It will be automatically generated whenever transaction is initiated, and whenever the transaction related output or input was generated. And especially this will be executed by the blockchain framework, that is Bitcoin blockchain framework. First, this op underscore duplicate will be pushed into the stack, because this script will be executed in the on the stack basis with the help of stack. So this op underscore dup will be pushed into the stack first. Next, next instruction will be pushed into the stack. That is op underscore hash will be pushed into the stack. Next, this hash value will be pushed into the stack. Next, op equal verify will be pushed into the stack. Op check signature will be pushed into the stack. Now the top of the stack will be pushed out. Check signature. Then you go for equal verify and get the hash value and get the previous hash value. That is which is there in the input. That hash value and this value are equal or not, you check it. If both are equal, then equal verify successful. If equal verify is successful, signature verification is also successful. So first these values will be pushed into the stack, and once these operations or instructions was pushed into the stack, then it will traverse from the top of the stack to the bottom of the stack, that is end of the to the 0 of the stack. Then each and every instruction will be executed and result will be pushed into the stack. It is just like your evaluation of postfix expression, in which the postfix expression will be taken, that will be pushed into the stack. Based upon the incoming operator, you will pop 2 elements from the stack and will execute, will perform the related operation, and whatever the resultant is there, that will be again pushed into the stack. So like that, the same operation will be done by this Bitcoin script, and we'll see discussion on this Bitcoin script afterwards. So this is the recipient address. This is the recipient address, and we'll see this one in future in the later lectures. So the UTXO is the amount of digital currency, that is unspent transaction input or output. UTXO is the amount of digital currency remaining after the cryptocurrency transaction is executed. So Alice is having 25 in account. Whenever he send 18 to Bob, whatever is the remaining, 7 is the remaining. So again 18 to Bob, 7 to the same address, that will be splitted. So here 18 is unspent amount, and 7 is also unspent amount. 18 is unspent amount for the Bob, and 7 is the unspent amount for the LEs. So UTXOs are processed continuously and are responsible for beginning and ending each transaction. When a transaction is completed, any unspent output are deposited back into the database as input, which can be used as a later date for new transaction. These are the transactions that are left unspent after someone completes a transaction, similar to the change someone receives after conducting the cash transaction at a store. So this is just like that. This is just like getting the balance after paying the amount. So this is what we call UTXO. The UTXOs in the block, for example, if you consider a block in the Bitcoin, this is the address where you can get this block. So these are the unspent transactions from where this transaction was formed to have 194.993 BTCs, and from this BTCs 0.50004 BTC to make this these are the transactions for combined date which are unspent and made to this one. Okay. And this is what the final total output 194,993.5004 BTC. Actually, this was added for as a transaction fee or maybe the miner fee. So this amount, so to get this amount, obviously these many unspent transactions were added to get this amount. So it is just like if you want to get some change in the store, obviously that store person will take several denominations, like whatever the free denomination is there, 10 denomination, 20 denomination, 50 denomination, 100 denomination. They will combine and they will give you the remaining, the balance amount that you are supposed to get. Just like that, from where it was since it is a digital currency and it's a shadow currency, they will observe from where you can pick up this unspent amount, and from that you can make the required BTCs. Next, we will move on to the how to ensure only user initiated the transaction. So far, we have seen whether Ramu is having the set amount or not. That is, we have seen that a particular person or a particular user is having certain amount in his account or not will be verified with the help of hash pointers going back to the blocks. Okay. And in this, we have seen how to split the transaction and how to merge the transaction. What is meant by unspent transaction outputs. Now we'll see how to ensure only user initiated the transaction. That means only the Ramu has initiated the transaction. So far we have seen only the balance checking, whether it really is having that amount or not. But now we are going to see how to ensure only that user is initiated the transaction or not. So obviously we know the digital signature concept. That we want from the signature is, so what we want actually from the signature is only you can sign, but everyone can verify. Just by looking at your signature, they can say that, okay, this is so and so person's signature. That is in a physical form. But in case of digital form, how you can do, that is with the help of digital signatures. So signature is tied to a particular document and cannot be cut and paste with another document. The digital signature will work like this. API for digital signature. This is a secret key and private key. A generate keys. So secret key and private key will be generated. SK is secret key and public key. That is PK is public key. Now signature is equal to sign off with the secret key on the message. So this message will be encrypted using this secret key of the person who is sending the transaction. Validation will be done like this. Verify, use the public key of the sender and take the message, whatever the message you have received, decrypt it and verify with the signature. Okay, if both are equal, then signature is valid, otherwise signature is not valid. So this is the way the digital signature works. So Bitcoin uses the ECDSA, elliptic curve digital signature algorithm. The elliptic curve digital signature algorithm will be used by Bitcoin and the curve used is specification 256K1, which is a standard curve. Set of points are like this, and it forms a group of 2 power 256. Secret key is ZQ, which is a random of 2 power 256 bits. Some random number will be taken as the secret key. And private public key is like this, the E range, a point on the elliptic curve multiplied by the secret key. So it may be of around 512 bits or 257 bits. This much length will be taken as the public key. And this public will be hashed. Okay, usually public key will be hashed to get the public address. And a message is M. Instead of sending direct message, this message will be hashed. So instead of signing with the entire message, this message will be hashed, and the resultant hash value will be signed by the secret key. So M is equal to ZQ, and hash of message will be taken. So what is this hash function? SH256 will be considered. So 256 bit length output you will get. So the secret key will be key will be used to sign this hash value. Signature is like this, R comma S. What is R value? That is signature value, signature of secret key comma message. So here message will not be directly used, message will be hashed, and the resultant hash value will be there, that will be taken here, secret key comma hash value of message. So here you will get this message digest is of around 256, and whatever the secret key you have considered is of 256. So 256 and 256 combined 512 bits you will be having this. So valid signature verify, correctness verify is correctness. How to check for the correctness? Verify of public key comma message comma sign of secret key comma message. If both are equal, then it is true. The signature is valid. And you cannot force the signature. The reason is you are going to sign this particular message with the secret key only. So who knows the secret key? Obviously the sender only knows the secret key. No one can know the secret key of a person. So unforgettably, adversaries who knows the PK key, that is public key, gets to see signature on the messages of his choice and cannot produce a verifiable signature on another message. The reason is they have only the public key in their hand. Even though adversaries knows their public key, they will be having only public key, but secret key is private and is known to you only. So they cannot guess secret key with the help of public key, because the public key and private key pairs are completely different. Public key may be drawn via the elliptic curve, but the secret key is of your choice. Which you want to use is your choice. Okay. So that is the reason it is not very easy to identify the private key. Now we'll move on to the next thing, that is double spending, mining, hash puzzles and all. So for this, we'll move on to the consensus in Bitcoin. So we have seen several consensus protocols with respect to the synchronous communication and asynchronous communication, and also we have seen the FLP85 impossibility theorem, and we have also seen that in the asynchronous communication there is a lot of chance to get forks using the consensus protocols. So conventional consensus protocols cannot be used for the public blockchains where many users are involved. You don't know at what time which user will enter into the system and will leave the system. So if you go for consensus, we have seen the transactions will be flooded as they generated in the network. So do you want to go for consensus per transaction? You want to give the consensus to every transaction? So it is inefficient because there will be too much flooding in the network, and also if you create a transaction per one transaction for every block, we all know that the block has to be flooded in the network just like that. So that means the entire network is heavily loaded only with this flooding. So that is the reason it is not a feasible solution. It is inefficient and too much flooding and more work to be done by the miners. Obviously, Bitcoin uses the proof of work concept for every transaction validation, for every transaction to achieve the consensus on every transaction, the miners has to do more work. That means here they have to solve many mining puzzles. So alternatively, we have another plan that per block consensus. Instead of having per transaction consensus, we'll go for block level consensus. While creating the block, the consensus must be achieved. That block may have some valid transactions. So efficient, this is an efficient procedure because the block will not be created for every minute or every half minute like that. There will be a certain time is there. In that time, that block will be created by getting some by getting the transactions which was generated in that duration. So it is somewhat efficient and useful as miner need to work for block creation. It applies over transactions to included in the entire block. So that is the reason in the consensus in Bitcoin, we are not focusing on the transaction consensus, and also Bitcoin also not focus on the transaction consensus. Instead, Bitcoin will focus on the block level consensus because it will avoid too much flooding in the network. And also per block consensus means miner has to work for one time to create a block, and where multiple transactions will be included. Instead of working for each transaction, multiple transactions will be executed for multiple transactions. If the miner work for one time, it is sufficient. So the basic operations in this mining process are this consensus process. So basic operations include validation transaction, gathering the transaction for a block, broadcasting a ballot transaction in the block, and consensus on the next block creation, and chaining the blocks to form an immutable record. These are the operations we all know that that miner has to do. There are two major roles for the participants. Participants that initiate transfer of value by creating a transaction. Additional participants will be there who are miners. They won't initiate the transactions. However, the initiated transactions will be listened by the miners and will pick those transactions. And we have seen while picking the transactions, the miners will not get these transactions in the order. They can get in any order. That is completely random in nature. So who picks on some transactions and added work for computation to verify transactions. And these transactions who want to verify a certain set of transactions, whatever they have received, they will use to broadcast those transactions and compete to claim the right to create the block. So who is having the validity to create a block? So they will go for competition because the miners don't know who they are. Okay, one miner don't know who is another miner. So because they will join with the public addresses, and those public addresses will always keep on changing. Work on reaching consensus by validating the block, broadcasting the newly created block, and confirming the transactions which are available in that block are included in the block. So this is what the roles available in the network. One is general people who generally rule the transactions, and some of the miners will be there who especially validate the transactions, and these validated transactions will be included in a block, and they will face a challenge. They will solve the challenge, and they will create the block, and this block will be broadcasted in the network. So here adding a block to the blockchain, that will be like this. So transaction added. So if the transaction is added, valid, if it is a valid transaction, then it will be this validated transaction is added to the pool of unconfirmed transactions. So there will be unconfirmed transactions, means those are not included in any block. So that pool of unconfirmed transactions, select set of transactions to create a block. So how this particular set of transactions will be picked, it is completely random in nature. You cannot predict in which order the transactions will be picked, and this selection of the transactions to a block will change from miner to miner also. A miner may not get, two different miners will not get the same set of transactions to create a block. That is also completely random. So miners compete by solving a puzzle. So as a miner, you are sitting here, for example, at this position you are sitting as a miner. So from a pool of unconfirmed transactions, you will get some transactions to create a block. Okay. So, and another miner will get another set of transactions. You don't know whether both are equal or may be equal, may not be equal. It may be anything. So they will also be getting, he will also be getting a chance to get to create a block. So he will also be given a hash puzzle. A puzzle will be given to that miner, and also the miner one who is sitting here. This miner also will be getting a puzzle. Whoever solve first, they will give the solution, and this block, whatever is generated by the blockchain framework. So that block will be broadcasted with the solution. So solved block broadcast. So verify the new block. Because once the hash puzzle is given, if they solve and give the solution, anyone can verify with that puzzle, because puzzle will also be identified. What is the recently generated puzzles and all. So this solved block will be broadcasted. So verify the new block, and the verification is done. Then this new block is added to the confirmed blockchain. So this is the way adding a block to the blockchain will be done. So Bitcoin consensus objectives. The main objective is which block to be added next, because miner may get one block for mining, second miner may get another block for mining, miner 3 may get another block for mining. So the main objective in this Bitcoin consensus is which block to be added next to the blockchain. So the main challenge in this is the miners do not know each other. So miners, because it is a public network, okay, the miners do not know each other, because miner 1 may sit in some other corner and miner 2 may sit in some other corner, like that. Consider 3 miners M1, M2 and M3 with different transactions listened and formed as a block. Maybe because of the delay, or maybe because of the latency, or maybe any other problem, all miners may not listen to the same transactions. So M1 is having the transaction like TX 15, 16, 18, 19. M2 is having 15, 16, 17. So you look at M1 has not listened 17. But M2 listened 17. M3 listened 17, but he didn't listen the 15, 16, 18 and 19. So he listened 20, 21, 22, 23, like that. So like that, different blocks will be coming into the picture. So now which block solution or corresponding thing should be added into the thing. So one solution is like this: broadcast the information and then apply a choice function. So these blocks will be broadcasted and apply a choice function, like traditional distributed consensus algorithm. Like in the Byzantine consensus, you might have seen there are 4 military army generals. They go for choice function, whether to go for attack or retreat. Like that, you apply a choice function and just traditional consensus algorithm and apply a choice function. That is one solution. Okay, it's also a fine solution. But this is having some problem, like internet is inherently asynchronous. So it's completely asynchronous because I don't have the bandwidth that another person is having. I may be having 10 Mbps bandwidth, another man may be having, maybe working with a mobile phone or maybe other thing. Or in some countries, this much internet facility may not be available. So obviously, the internet is inherently asynchronous. So thereby you will get some delay. How much time, once after sending this block, but how much time this miner has to wait for confirmation? If any of the network was disconnected or maybe joined, you recall the FLP85 impossibility theorem. Reaching to a consensus is very difficult. So how much time a miner has to wait after broadcasting the information? So there is no definition for that, or there is no defined time to wait for. So next one is miners do not know each other. If anyone want to pick up the phone call and ask them whether you have confirmed or not, because miners don't know who are there in the network. So because of these problems, this approach is not suitable as there is no global clock. So there is no global clock in this, so that is the reason. Just to recall FLP85 impossibility theorem, if there exists breakage or network failure or any other thing, it is very hard to reach consensus in such networks. So that is the reason we'll make some more observations and we'll think of any other possibility is there or not. First observation is any valid block, a block with all valid transactions can be accepted even if it is proposed by one miner also. Okay, that is also a good solution. We can also make this particular thing. The protocol can work in rounds. Otherwise, broadcast the accepted block to the peers and collect the next set of transactions. If it is keep on doing that, then there may be some malicious attackers, malicious nodes. They may disturb the network by proposing the fake or some transactions which are known to them. They can do anything in that. So this is also not a thing here. So we'll go for one solution for this. Every miner independently tries to solve a challenge. Instead of sending this, every miner independently try to solve the challenge, because everyone will be having some set of valid transactions and a block formation. If they have solved the challenge, very good. And they can, once they solve the challenge, they can also send the answer along with the newly created block in the network, so that other miners can easily verify whether he really solved the challenge or not. So that challenge must be like this: the block is accepted for the miner who can prove first that the challenge has been solved. So whoever solves the challenge first, that particular block will be added to the blockchain. That is what the condition with which we are moving forward. So here block is accepted for the miner who can prove first. That is, here we are there for that fellow is performing the proof of work here, that the challenge has been solved. The challenge, who will give this challenge? Challenge will be provided by the blockchain framework or network. So that framework challenge will be solved by the miner. Whoever solves this, that fellow's block will be added to the blockchain. You look at here, M1, first M1, M2, M3 are there, 3 miners are there, and 3 miners have the respective listening of transactions and block. Now assume that miner 1 have solved solution. So here he said that I have solution, and he informed M2 and M3. So what are the transactions are there in this M1? 15, 16, 18 and 19. So M2 has 15, 16. There is no 17, okay, which was approved here in the created block. And M3, 17 is there, 20, 21, 22, 23 are there, but this 15, 16 is not there. So everyone has seen that TX 18 and 19 have been committed, but TX 17 is not committed in the committed block. Okay, so TX 17 is not there in the committed block. So now what will be happened is hence this TX 17 will be included in the next round. Now 15 will be eliminated, 16 will be eliminated. Now next time the miners want to create a block by eliminating 15, 16, 18, 19 out of 17, 20, 21, 22, 23, and the transactions that was generated up to that time, and what are the leftover transactions that are not available in that are not included in already created blocks. All those transactions, from that again, that will form the pool of transactions. Okay, that will form the pool of unconfirmed transactions. From that again, some randomly some set of transactions will be generated. Will be collected and form it as a block for each miner. Now each miner will be given different hash puzzles. Now the miners has to solve that hash puzzle and have to deliver this particular result into the network. Okay, whenever all other miners will listen to this network, this solution, and if they confirm that okay, this solution is very easy, this solution is a valid solution, then whatever the transactions which are available in that confirmed block will be accepted, and remaining will be joined to the unconfirmed pool of the transactions. So in this way, you cannot predict whether your transaction will be included in the immediate next block or not. And that is the reason we have seen in the last lecture that to get your block is confirmed or transaction is confirmed, you are supposed to wait at least 1 hour. So this at least 1 hour means you should have so much patience to get confirmation from the blockchain that your transaction is included in the block. So this is the main problem with this blockchain. So blockchain throughput is very slow, throughput is low, and also scalability is also is not there.